Hi, my name is Danny Doming. I'm a general dentist in Lafayette, Louisiana, and I'm going to lecture on the restorative evolution for full upper arch. Basically just a digital step-by-step protocol for full arch, angulated screw channels, and 3D printing, milling, hyperdent, exocad. Let's get into it. You can follow me on Instagram at Implant Diplomat, and also check out the Facebook group Implants in Black and White. So this is I developed the Vortex full arch angulated screw channel screw, right? I've used several screws in the market, saw the flaws with them, and eventually I was able to work with a team of engineers to come up with the current screw design that we've been using for the past 4 years and had great success with it. Recently teamed up with Rowe Dental Lab to create the grammetry powered by Vortex screw for your arches, and we'll talk a little bit about the Opti-splint protocol and the Vortex screw with grammetry. So, but before I want to talk about the desk screw. So the desk mini screw, or the Noble Bio Classic mini screw, the small micro screw that we used to use. You would whenever you would use these for full upper arch, because they were used for full upper arch, you would have 0.4 millimeters of material underneath the screw head, but you would engage 4 turns into the multi-unit abutment, which is important. So whenever you screw a screw into a full upper arch, it would actually, whenever it torques down, you need 4 turns inside the multi-unit abutment to be able to rigidly fixate and prevent the screw from backing out, prevent the screw from loosening. Like, I know people have heard screw loosening is an issue. You just need the minimal amount of turns, which is 4, to get enough preload and clamping forces to be able to hold down your full upper arch and prevent the screw from backing out. We'll talk more about that in a little bit, but just to introduce that concept now. Again, the issue is not enough material underneath the screw head. You would have 0.4 millimeters of material, and eventually it would fracture. The other issue I have with the screw is it is a butt joint screw. The head of the screw is 2 millimeters, the threads are 1.4, but you only using 0.25 millimeters of radius of this screw head to hold down the full upper arch. That's not enough material, and that's a lot of pressure on this screw head, and eventually you would have fractures of the screw, right? So let's get away from that. And then so this is on the left picture is the mini screw, and this is the longer screw. So this was like the answer to all of our problems, to be able to create a longer, taller screw where you could get more zirconia and prevent the fracture of these upper arches. Now the issue with that is this screw, even though it was taller, I like this idea where you put more zirconia. So this is basically the multi-unit abutment here, this is the screw head. So this is the amount of zirconia you would get underneath the screw head, and it's 1.4 millimeters is the exact amount which you would get underneath. And to demonstrate that a little bit more for us is our colleague Horst, who invented the iMetric. He's going to give a little talk about the different screws.
That's the geometry that would be used if you use this direct, yeah? And 34, that's what it looks like for the tie base from this. And 36 is basically the same with the library from us, we use the same screw. And 42, this is this long screw. So on 32 you have like 0.4 millimeter space between here and the air, so you have 0.4 millimeters of printed material, and that simply rips too easy. And with 42 you have like 1.4 millimeters, yeah? And that gives you a lot more space, and a lot of people use that. And they simply buy the longer screw from this, and all the design and everything is existing here. And then Rosen, he developed this screw, which is sort of conical and works with the friction of the whole head here, yeah?
So basically he was talking about, this video is an old video, but this is the 34 is the desk screw with this tie base, right? 32 is the same desk screw but without a tie base, right? So this is the zirconia. He was saying 0.4 millimeters underneath the screw head. So they came out with the 42, which is 1.4 millimeters, which he was saying was much better. And he was saying then recently, or this was again a while back, because Dan Rosen's screw's been out for a long period of time, but this screw holds down from the lateral wall. So this is a butt joint screw. This is 44 is holds down from the lateral walls. You can see 0.2 millimeters of radius for a butt joint isn't as great as more walls of retention of your screw, right? So I hope that concept rings clear. This is the Dan Rosen screw for full upper arch. This is actually his original design here, but he was smart enough to thicken up the screw to prevent fracturing of the screw head, because he knew there was a lot of tension on the screw. So this was his screw. He talks about how this holds down from the lateral walls. This technology and this technique and this screw and this concept have been out for a long time in Prosto. So it's not a new concept for us. Dan was just smart enough to, get a patent on it for a full arch. So again, the mini screw would cause some fractures of zirconia because there's not enough thickness. So to prevent the thickness issues, we're holding down from the lateral walls, right? But he's also saying you can't torque these out. You can only use hand torque pressure to put these in. But it wouldn't give you angle correction, so you couldn't mill angulated screw channels. There was a screw that came out with the ability to mill angulated screw channels, right? And it was a taller screw, but again, it went back to the butt joint where the screw was holding down the apex or the bottom of the screw. The other issue I had with this screw is that the final drill for the hyperdent profiles is using a 2mm diameter screw to be able to mill that out, and that would weaken the zirconia, and you have these really big fat holes to be able to fit the screw through. And you can see these are really massive holes compared to these holes. So this is the screw that I came out with, the Vortex screw for full upper arch. You can see how tiny these screw holes are compared to this screw. Now, this is the weakness of this full upper arch. All of these screw holes. So the more zirconia, can you imagine having a wide 2mm around this hole right here? It's just going to fracture. There's no way it can hold up. So you have to make these big and beefy whenever you use this screw, and on this one you can have them a little bit more delicate or look a little bit more like natural teeth. Even if you wanted to go FP1, that'd be conceptual. So obviously the market was moving over to angulated screw channels for full arch, and Des came out with a concept to mill a flat surface at an angle. It is don't ask me, ask your lab tech if it's easy to mill a flat surface at an angle, and you'll get your answer. You can only go up to a certain amount to be able to get this predictably, and it's still very difficult to do. So, and then this is the Vortex screw. So this is the Vortex screw, and this is the Des tall screw, right? You can see the height of this screw compared to the height of this screw, right? So underneath our Vortex screw, you have more material, just like the Des long screw, right? Just a comparison analysis. And then this is just the mini screw versus the Des long. So you can see 0.4mm of material at the screw head, 4 turns, but this is 1.4 actually, or 1.2 underneath the screw head, and 0.25. But the 0.25 radius is still a killer for me in these butt joints. If you want to learn more about the Vortex screw, this is the screw here. This is the 1.4 and the 1.6. Click on this link right here with your phone. You'll be able to watch a free video that'll take you to a YouTube channel, and it's about a 5-minute video to kind of go in depth of the advantages of the screw. But this is the screw here, and this is it. So it uses a T5 head, and it's got this hyperbolic head where you can hold down from the lateral walls and the apex of the screw and be able to mill from angulated screw channels. Now what we perfected was, so we drew this screw in some software, we had a machine, we tested it, we drew our exocad profiles, and we even drew the hyperdent template to be able to mill these things. Because what I wanted to do in a marketplace, whenever you're milling these things, you get some really loose tolerances with milling, and I didn't want to have a screw going down a hall. What I wanted is a very tight tolerance. Now this is a very predictable milling profile for hyperdent, so we have a template generator that we created for this. So if you use this Vortex screw and you import the Vortex geometries into your hyperdent library, every time you take a full upper arch and you import it into hyperdent, those calculation tool paths to be able to mill it, it'll automatically recognize the screw, and it already had pre-calculated tool paths. So the calculation times are going to be faster, and the results of your milling are going to be tighter and better as long as you have the template generator. And if we can provide that for you if you ever need, just reach out. If you're going to mill in your office, or if you're going to work with a lab that uses these, most major labs have the template. If they don't, they can reach out to me and I'll give it to them. So we have 3 different screws. The 1.4, which is the Noble biocompatible screw for these arches. The 1.6, when the only difference between the 1.4 and the 1.6 is the radius is 0.1 millimeters wider here and here. So 0.2 millimeters overall for a diameter. And this is the Riddle Dental concept. They came out with the first one. and a couple of manufacturers got on the market and started using these. So you can also mill both of these for angulated screw channels, for direct to multi-unit abutment, using tie base, and for zirconium substructures. And we're coming out with a 1.72, which is the implant direct screw. This is soon to hit the market, hasn't yet fully. Again, this is a driver, so this is our T5 driver, and this is our screw, and this is an angled tool path channel for a FP1 crown, so a single tooth crown. This is our head. You can see it's a lobular shape and form, and you can see how the growth of it. So this is the apex of the screw, and these are the threads, and then this is the bottom of the head, so right here, and then you can see as it tapers out to get to the top part of this screw head, that's this outer diameter here. So you can see it's a gradual curve out like a hyperbole. It goes underneath and then out, and this is how it holds down the lateral walls of the screw. Again, this is the T5 driver, so it's a ball-in T5 driver is used to torque these out. Very compatible exactly compatible with the Megagen AnyRidge. Just to note, Noble Biocare is a T5.5, and Strom is actually a T6. So for those that need to know that information, this is the T5 driver, and this is the tight tolerance of that screw. And this is a very predictable, even with tool wear, you can predictably mill these angulated screw channels and direct channels. So this is a direct mill, and this is a angulated mill at 22 degrees. And you see there's 1.4 millimeters of material underneath the screw channel, thick enough to prevent fracture of your zirconium. Just a quick little chart to show you all the different features of all the different screws in the market, and we basically tried to research and figure out what was the best screw, and that's what we came up with. But we wanted to be able to mill direct to multi-unit abutment, so your full zirconia arch will sit on this multi-unit abutment, and this screw will tighten into the zirconia, cause clamping force and preload to be able to tighten up this arch, and you can see it can milled at an angle, and this screw can be used at an angle and it's still unscrew this. It's a Torx head, that's all it is. I didn't embed the driver, I just used the Torx technology in the head of the screw to be able to develop this. What I did include is, so this driver is stainless steel, and it's heat treated stainless steel, so it's really very, very strong. But I did create a weak point on the driver, and the weak point is if you try to over torque the screw, sometimes you'll get screw fracture, right? Because the threads of these screws are only 0.4 millimeters, like it's gonna fracture. You can't over torque these things to 35 Newton centimeters like you can with a 1.8 screw. So what I didn't want to happen is somebody torque out this screw, it fracture into the multi-unit abutment, you have this full upper arch that you've already delivered, and it's catastrophic issues where you have to take out the upper arch, take out the multi-unit abutment, replace the multi-unit abutment, replace the arch, and then just have tons and tons and tons of issues. So instead of the screw fracturing, the driver will actually fracture. It'll break after 15 Newton centimeters. So much easier to replace a $40 driver than a whole upper arch and a multi-unit abutment and all the components that go along with it. So just as a fail-safe, these drivers will fracture or distort. Even heat-treated stainless steel will fracture. Then we also have the tie-base interface, where there's a lot of purists on the market that want an angulated screw channel but still want to use a tie base, and we have that option to be able to use these tie bases with angle corrections. We can talk about cost of the screws compared to other screws in the market and the value you get out of each screw. And look, I've got a lot of money in this screw with a $50,000 patent, trademarks, software that I used to design it. You know, I had to buy 50,000 screws to be able to fulfill, just have like enough screws in the market. Like, you can't go to somebody and say, hey, give me 10 screws and manufacture. They won't do that. You have to order a certain quantity of screws to be able to actually start selling these. So yeah, we're FDA compliant. We have FDA 510K packaging requirements. Like, we've done all of our homework for this screw. But just understand, I'm not going to retire on this screw. The screw is, I'm not going to make millions of dollars off of dentist on this screw. If you want to buy 10 screws, yeah, it's going to cost you, $30 a screw. But if you want to buy, a massive volume of screws and you want to incorporate the screw and you're doing a lot of full arches, then yeah, you're going to get, you don't need that much support from me, and you don't need that much help from me, and you're going to take off to the races. So yeah, you get a massive discount whenever you buy more of these, right? So you can get them for very inexpensive compared to other screws in the market, right? That's all I'm trying to say with that. All right, so the concept that we talked about is direct to multi-unit abutment, so without a tie base, with a tie base, with angulation corrections if you want, and any type of substructure you want. You can use titanium, chromium cobalt, Trilor, Preet, whatever you want to use. You can use that as your substructure, and you can have a superstructure on top of that, whether it be composite, milled PMMA, or zirconia. And I'll show you some case examples in a little bit. But all of these can be milled without a tie base and with a titanium bar at all angle corrections, 15 degrees predictably. You can get up to 20. It just depends on your milling profiles and all the angulations of your arch. So we always say just 15. 25 with the angle tie bases and 25 degrees with the titanium bar substructure. So again, direct to multi-unit abutment, straight and angled. Tie base, straight and angled. And custom titanium full arch bars, straight and angled. You can actually mill an angled screw channel in these titanium bars, and I'll show you some examples of that in a little bit. But the screw, just know that the screw holds down from the lateral walls and the apex of the screw head, and you have 1.4 millimeters of material underneath the screw head for your full upper arch is what you need. So let's see, 1.4. Oh, so that's the concept. Understand that. You have 3 different materials that you can mill this in, not just direct to multi-unit abutment, and you can angle correct. So you can angle correct in all 3 of these mediums, and you can go straight channels, but you can use it with a tie base, without a tie base, and with a titanium bar. All right, let's get into this next concept. Prosthesis types. So if you're FP3 and FP1, there's going to be a difference in the screw channel height, all right? Because your crown's not going to be as tall as an FP3, so you're going to have an FP1 crown, right? Well, that definitely changes your ability and what screws you can use for your full arch, and I'll get into that in a second. I'll show you some examples. Let me just introduce this concept. So what we've talked about is the 1.4 millimeters underneath the screw head of material of zirconia. And at that, you have 4.25 turns, so a little bit more turns than you actually need. The minimum's 4. You have 4.25, so you get a little bit more turns, more tension, right? More fixation, preventing screw loosening. At 1.2 millimeters, so you can actually change. You can see the depth of this screw compared to this screw. So it's 0.2 millimeters deeper in this. So now you have 0.2 millimeters of material underneath the screw head. You have 4.75 turns. At 1 millimeter, you have 5.25 turns. So now you have 1 millimeter material underneath the screw head. And at 0.8, you have 5.75 turns. So more retention, more returns, more turns into the screw. Now, why is this important? I'll get to that in a second. Just know that you have 4 different modalities to be able to change the height and the amount of material underneath. I don't want people to lose this concept, but typically I use the 1.2 or the 1.4, and every once in a while I use the 1 millimeter, and I'll show you why. And what we talked about is clamping forces and preload. So this is what preload is. Preload is the tension created by the fastener, which is our screw, when tightening. So pretend this is our Vortex screw and it's squeezing down. This brown stuff is our zirconia. And down here at the bottom of the base of this is our multi-unit abutment. So as you screw down this screw into the multi-unit abutment, the threads engage the multi-unit abutment, and now they're pulling up the zirconia to the screw head, and that's where you get your clamping from. So the screw head to the base of the multi-unit abutment, and it's squeezed in between with zirconia. And that preload, that initial load that you put on the screw, that torque force of 15 Newton centimeters will actually prevent the screw from loosening. All right. And again, you can mill that at various depths: 0.8, 1, 1.2, 1.4, and you can see the various. This is all the multi-unit abutment heights, and this is the base of the screw as it goes up. All right. So Now what I'm going to do is show you a comparison of the desk screw on top of the Vortex screw. So this is the desk screw, this box right here. You can see the diameter of the screw compared to the Vortex screw. Now this is what I got from exocad. So basically this is the milling profiles. This is not the exact screw itself, but it's the milling profiles for the screw. So this is where the screw would seat inside the arch. So you can see that the Vortex screw actually has more material underneath the screw head at 1.4 than the desk screw. You can see at 1.2 it actually has the exact same material. All right. You can see that the one has a little bit less material. So 0.2 millimeters less material underneath the screw head. Again, just comparison the desk with the Vortex screw, just to show you the material underneath the screw head. And this is 1 and this is 0.8. And all this really becomes very important when you get into FP1 cases and small teeth, small mouths, where you don't want to have these big holes and you need angulated screw channels. But also, that's direct to multi abutment. But also, what if you want to mill bars with angulated screw channels? Well, if you have an overdenture, it's really not that important. But you can mill angulated screw channels with these screws in this full arch bar. It's what I call it is engineering simplicity, right? You want one screw for all of your cases, whether you're doing direct to multi abutment, or you're doing tie bases, or you're doing full upper arch custom titanium bars. You want to grab one screw. You don't want to have 0.48, 0.5, or forget what screw you have, forget what driver you have. Don't have, you can't have every single driver for every single system. It just doesn't make any sense. But what if you have a full upper arch, right? That's too big for zirconia. So the arch, the guy's mouth is so large and the teeth are so large, it doesn't fit in the puck. And in this case, this guy's got pterygoid implants. And he's got a massive mouth, and we're doing second molars. But I can't mill this whole arch in a puck. This won't fit. And he's a clencher and a grinder, and I need some substructure, or I'd like to have some substructure to prevent this thing from fracturing. So then I'll introduce a titanium framework as my substructure, angulate the screw channels out of the facial aspect if I need to be able to get them out of this facial aspect, so whenever I mill this full upper arch, it'll have an angulated screw channel, and I'll still be able to torque out each one of these multi-unit abutments. And again, you can also use these with tie bases. You can see this angle correction. You can see how far out facially this multi-unit abutment is facing, and it should come out the facial aspect of this implant, but because I can angle correct the screw channel, it's going to go down and in. And actually, to use tie bases and a bar for this case, I did a combination of both. So that's the different features. Now let's talk about FP1. Now FP1 is a little bit more complicated when you're talking about screws. So this is the desk short that we talked about initially. This is the desk long screw. Now, see, there's not enough material except for the 0.4. Again, we understand that concept. It's not feasible. So we could use the desk long, correct? Well, look, this is minimal thickness. So the minimal thickness of exocad for this arch is going to bump out this. You see these little bumps for this FP1 case? So exocad will be able to use this desk long to create this upper arch for FP1, but whenever you mill it, you're going to have these little bumps come out. And after you mill it, you can actually shave this down in green state and then center it. But then once you center it and put it in the patient's mouth, these screw heads are going to be sticking out, and you're not going to have enough material to put your Teflon and then your composite on top. These screws are going to stick out the arch. And this is the minimal thickness. So you can see the material underneath this desk screw. So this is not a very good screw to use for FP1. And in this particular case, this is what it'll look like. You'll get a bump out of zirconia, because you need a proper thickness around the screw heads, because the screw is going to seat right here, and then you put your material on top of here. But you can't have these bumps on your on your arches. So this is just a comparison between the desk long screw. Now let's look at Rosen screw. Now Rosen screw is a very tall screw, and you get the same effect with this screw, same minimal thickness effect. I'm going to show you the actual height of the Rosen screw. So this is the superimposition of both screws on each other. You can see that Rosen screw is a lot taller, especially here. And this is how they both sit in a multi-unit abutment. So this is the multi-unit abutment here. This is the material underneath the Vortex screw, and the material that you would need to cover this screw, and then the material on top of that to be able to put Teflon and flowable material on top. It's a very tall screw and very difficult to use for FP1. Same thing with this screw that we talked about earlier that can mill angulated screw channels, but the channels are really, really wide in diameter because you use a 2mm drill to cut out this orifice. The screw is actually sticking out of the prosthesis, so not a great screw to use for FP1, right? And again, just a comparison side-by-side analysis. Yes, you get more zirconia underneath the screw head, but the screw head is way up here, right? So this is a superimposition of both of the screws. And again, the screw head of this other angulated screw, see how much wider it is? And the screw head comes out and goes all the way up here. So it's a big screw. So the Vortex screw is great because you can mill it at various angles, 0.4, or various depths, 0.4, 0.8, 1, 1.2, and even 1.4. What if 1.4 doesn't work for this one? Well, you can change that 1, you can back that one out to 1.2. You don't have to change every single screw in the full upper arch. If 1.2 doesn't work, well, you can drop that down to 1mm. Just change that one screw to 1mm. Or you can change them all to the same depth. It doesn't really matter. But if you have one screw if you have a tight bite, patient with a tight interocclusal distance, small mouth, and you need to use a screw with an angulated screw channel, and you change the depths, this is the screw that you would need for that case. And let's look at this case because this is kind of interesting. This is a full upper arch bar that we milled for this one guy, and it's neat because the full arch did not fit and he wanted second molars. So we milled the second molars inside the titanium substructure. You can see here, so this is a titanium substructure with second molars, angulated screw channels using the Vortex screw. So you can see he has second molars in the lower arch and he wanted them for the upper arch. So this bar gets milled separately from the zirconia that gets stacked on top of it, and it gets centered and he gets second molars that can fit. He's just a really big man. And this is just a quick video to show you how to angulate the screw channels whenever you go on direct to multi-unit abutment, and I'll show you a little video how to use it. You basically just deconstruct the parts and you change the screw channel angle, and you can actually just mill the screw channel angle at whatever angulation, that correction that you need for your arches. And then now you can see the angulations of those channels. All right. And you can also do that for titanium bar substructure. So here's a titanium bar, typical bar, and we can mill this at an angle. And again, you can mill through the titanium, and whenever you construct the final prosthesis, the superstructure that goes on top of that, the PMA or the zirconia, you can actually mill those angulated screw channels inside there, and it still seats the same. Now for these titanium bars, you can change the depth. We use 0.4mm because it's really all you need. You can change to 1.8. You can do whatever you want. So that's really the concept, and that's why Grammetry Opti-splint has the market on full arch. Look, I have iMetric. I love iMetric, but just last week my iMetric went down because the dominoes were worn out, and I had to get some overnighted. Well, the patient was sedated in my chair, and I needed something. I called iMetric support. They were super cool about trying to help me. Worked on it for about a half an hour. Gave up. I have a couple Grammetry kits in my office. I literally popped in the guy's mouth. It took me like 5 minutes. I luted everything together. Got the patient out of the chair. He was able to come back the next day to get some provisionals, and I'll show you his case in a second. So Grammetry, powered by the Vortex screws. So every time you order a Grammetry kit, you'll get some Vortex screws. You'll get a Vortex driver, and you can order these hubs if you want these hubs as well. And you can use a manual torque driver, like a hand torque driver, to be able to torque these screws out at 15 Newton centimeters for your full upper arch. Now, what's the Grammetry kit, the Opti-splint? What does all that look like? So if you buy a kit, this is what you get. You get all these Opti-splints here, 6 screws, some handles, and frames. Basically, each one of these little Opti-splints gets screwed into each individual multi-unit abutment, and you take these wireframes and seat them on top of this area, and you lead it all together. And this is kind of like your verification jig. You can scan these in the mouse, but it's not as accurate as scanning on a tabletop scanner. So I do scan these in the mouse. You don't have to, but I do. And I take them out to be able to stitch them outside the mouth using a tabletop scanner. Or you can just mail them off to your lab to get an accurate fit. So this is the lower this is the lower pre-op. So this is not my case. I actually helped somebody restore this case, but this is the intraoral, this is the lower arch. I removed it and I scanned the tissues. So my protocol for this case would be to if this lady's vertical is correct, scan her upper arch, scan her lower arch, like in the upper left photo, and scan her bite, left and right side bite. And that would give me my vertical dimension for her. So to be able to cross mount that, I would remove her provisionals and now scan her tissue. That gets cross mounted back. Now I Opti-splint and Opti-splint scan, which you see here. And then I'm able to redesign and reprint her a lower arch to try in, and that's what you see here. So this is just a side-by-side compare analysis, preoperative soft tissue scan, Opti-splint scan. Again, you can scan this in the mouth if you want to. It's not necessary. What's really important is that you get this scan on a tabletop scanner for more accuracy. All right, and you get that. So this is, once I just tack it in the patient's mouth with a little bit of old composite, and I'll unscrew it, and then I'll just take a bunch of cheap jet acrylic, and I'll just load that thing up. So I don't want this thing to move. If any of those move, it's not accurate. It's not going to fit proper. And all I did was just cross mount. So I cross mounted the Opti-splint scan with the provisional scan with the soft tissue scan. Actually, this is the Opti-splint scan intraorally with the Opti-splint scan, or the grammetry scan on the tabletop scanner. And this is superimposition of all of them, and this is superimposition of the provisional scan with the final design scan and the Opti-splint scan all in one. So let's look at a patient case, all right? So this guy comes in, and that's a smile. That's his exaggerated smile. So I usually take two photos, smile and retracted. But now I'm taking exaggerated smile just for this one reason here, just to see if they show any pink. And his case is unique because he has already 6 implants in his maxilla. His front 4 teeth are decayed, and he just needs those teeth out and needs to be converted. We can't remove bone anymore because the implant's already in position. We're really just here to convert him from natural teeth to implanted teeth and take out his, and we're going to do the same thing for the top as we are for the bottom. So my protocol for a case like this would be able to take these 3 photos just like this, and then I take intraoral scans. So I take an upper and lower intraoral scan and a bite scan, and I do this if the patient is, their CR is correct. If it's not correct, then I take a CR bite. I'll tell you, I had lots of issues with bites whenever I think patients are in a stable occlusion and they're actually not. So if I can tell that they're not, I take CR bites. If I'm unsure, I take a CR bite. And if I'm not able to get to the room, I just have my task take a CR bite, so I know that the condyle seats fully in the fossa, and I'm getting a really good bite, and I can recreate their bite in exocad. And this is the upper and lower scan. This is just from our Medit scan, and this is his bite before and after, or before. Now what we're gonna do is send all this information out to the lab. And what the lab does is they take the photos of him and stitch it to his teeth, and then his teeth get mounted on an articulator. Right? I use a penitent articulator and make sure that I go through all lateral excursions to make sure this thing's mounted properly before I start my surgery. My surgery is pretty easy for this case because the implants are already in. But I'm going to show you like the walking through the concept for this case. So you have to have common stitching points, kind of like we did when I first showed you the Opti-splint. So I'm removing the crowns from these. I have an intraoral scan of the upper arch that's already taken. I'm removing the back teeth crowns, putting in multi-unit abutments, and scanning them with these 6mm multi-unit abutments, scan healing abutments. I'll show you what those look like later on. These are my favorite ones on the market. They work really well for FP1 and FP3. They're just the best universal scan body that I've used. So the common stitching point for this guy, you can use fixation pins if you want to, but I'm going to use his teeth as a reference. So his teeth are going to be my reference. So these 4 front teeth, these 4 front teeth are going to be my common points. Now, once I take these last teeth out, I'm going to recontour the tissue and the bone in this area to stay FP1 and prevent his pink tissue from showing. I'm going to reduce some bone and contour the bone in this area and take my final scan. All these can get cross-mounted and cross-stitched back. So I'll send this off to my lab, and they're going to wax up his teeth, right, from his original scans. They're going to wax up his teeth and remount it and make sure everything looks good, and send me the STLs, and I'll just 3D print them. And I did that for his upper and his lower. So this is the day after surgery. This is the very next day. See, he's not even that swollen, but his lips are a little messed up from the day before the procedure. This is provisionals, before and after results. Just some side profiles of his before and after results. This is his Panorex before and after. And this we printed on a Sprint Ray printer, a P55S, the new printers, with Sprint Ray on X Tough at 100 microns, and it took 35 minutes, and then we can deliver this. And that's the whole Opti-splint protocol, which is great. If you're using iMetric, that's great too. There's actually a library for this screw. It's called the Levy library. You can use 0.2 millimeter seat or whatever seat you want. If you don't have this library, I can send you a video on how to use it and send you the library itself, or just reach out to Transcendental and ask them for it, and they can give it to you. Yes, we are FDA compliant. Yes, we're registered. Yes, we have our supplier quality agreement. Yes, we're manufacturing an FDA approved facility. All this is ensure supply of our quality for ISO. We have everything you need that's standard for whatever. Yes, we are trademarked. Yes, we are patented. All that's been done, right? I know I get this question asked ongoing, nonstop. And the reason why we came out with the name Vortex is because the milling pass this thing takes in the hyperdent just reminded me of a vortex, and the name kind of stuck. And ironically, I was just in Sedona my wife just turned 40, and we're in Sedona for her birthday, and all I heard the whole time in Sedona was the vortexes of Sedona. It kind of made me crack up. You can see how this is the drill pass, and it doesn't matter what material it is, PMA or zirconia, but this is the pass the drills takes to be able to mill out zirconia, or PMMA. Just goes in all these concentric circles over and over again. Again, these are template profiles, so I have all of this saved, and whenever you import a full upper arch, it calculates relatively fast. And I think I'm going to show you a quick little video on what that looks like. Let's see if I can get this thing to go. So this is hyperdent, and I think this is an angled mill channel. So when it first starts out, it'll mill from an angle, and you get further down, further down, further down. Let's see if I can speed this up because it's a long video. Just to show the accuracy of the milling and show how capable it is milling. And actually mill in there too. Another thing to note is, and then it'll come back and remill the top orifice of it to make sure it has everything. Now we use a carbide round 1 millimeter burr to mill this, and we also have a new T-cutter burr that will actually mill from the cavity side into this area heel to make sure that you're getting everything out and there's no preload screw impingement. And this is just another video of it milling direct to the multi abutment, or with a straight changeable, no angles, straight. We do have hyperlint templates, so important. Get your lab to use those. So this is the one-piece scan multi-abutment healing abutment. It's a healing abutment for your multi-unit abutment, and it's also scannable. So you can actually scan this and use the library in exocad to be able to calculate, to be able to design your full upper arches, right? Tie-based technology has changed a lot. Very quick on this. You know, these high slope profiles weren't very retentive enough, so we made them taller over time, but this was causing fretting. So then the the tie base that we currently use has a tighter tolerance with a taller interface, and you can mill these at angulated screw channels. But what case problems have I seen? I have seen some issues with these. I've been doing this for 4 years now. You have to use the proper exocad library to create these. So make sure you go to the exocad's website. It's a verified library. Download the library. It's free. You can have it. You can't take, like, I had a guy ask me in a course, hey, I have this case that I designed a long time ago. I really want to use your screw, but can I just replace the screws that I have in now with your screw? And the answer is no, because your full upper arch is designed and milled to fit that screw and that screw channel. Our screw channels are very, very tight, and there's a better tolerance for them, and you can mill them at angles, and there's a seating for them that's proper. So no, you can't switch out old screws with these new screws. Whatever screw you mill to, that's the screw you're stuck with. Like this case in the top right, actually had a guy reach out to me and he said he's having issues with my screw, and the designer used tie bases. So this is the desk tie base, and he said whenever he went to screw in, it wouldn't seat properly, and he was frustrated. Well, whoever designed this case for this dentist used a different library, and it wouldn't seat. So make sure you use the proper library for it. Or whoever's designing for it, use the proper library for it. Only use this torque wrench. This is the only torque wrench I use. I had a lady that was using her implant handpiece motor to torque out the screws and fractured off a couple screws. That was a problem. Broke a couple drivers. For the screws, I use the screws over and over and over and over again in my provisional phase. So every single temp that I usually do 2 temporaries. Sometimes I'll do 3, depends on the case. But I'll always reuse those screws over and over again. But for the finals, when you're going to finals, I always use brand new screws for the finals. Again, hand torque with a driver to 15 Newton centimeters. Do not use anything motorized. I am coming out with a delivery and a retrieval tool that is very friction fit, and it'll hold the screw in the driver, or the driver in the screw. You can get severe angles if you want to. One screw for all of your cases instead of multiple screws. That's really what I wanted, simplification for my life and my full arches and for the rest of my career. Printed arches, what I'll see a lot of times is you'll print an arch and you'll get a little piece of resin inside the screw access hole, and when you cure it, the screw will bind prematurely. So I take a 2mm round or 3mm round burr, and I'll just drill out that screw channel, clean it out, and I'll be able to bring my screw to depth. That's for printing. For milling, contact Follow Me North America, Hyperdent. They have templates that we created for the screw to get really tight tolerances. But for FP1, this is what I want to do. I want to use FP1, change the heights of my multi-unit abutments, change the heights of zirconia underneath my multi-unit abutment, and get really predictable results, and get really nice tissues, and not have to mow down bone. Like this lady had a really high smile line. I wanted to give her a pretty smile, and I wanted to stay FP1, and I didn't want to mow down her bone. All right, what else? What about cases where you got a pterygoid off here, or this is my canine, so this is my first bicuspid, and this is my third molar back here. Well, this is a long span for zirconia, not expecting it to fracture. And for these, if I have long pontics, I'll add a titanium substructure into my arch. And I still want to be able to mill angulated screw channels. So this is a good reason to be able to use this screw and be able to mill a titanium substructure for your arch. All right, and this is the case that we delivered for him, his upper and lower, before and after results. Right, and it's a long span from this tooth all the way to the back. So this is the canine premolar all the way to the back here. It's a long span and not to expect it to fracture. So I put a titanium substructure in there to prevent it from fracturing. I'm running out of time here, so I better speed it up a little bit. What about a patient that you did teres, zygos, and an anterior implant? You have long spans of pontics. You're gonna need a titanium substructure of some sort. I mean, these implants are not spaced appropriately like we're commonly used to. The zygos are 40 millimeters all the way traversing lateral sinus to the zygoma. Again, shout out to Dan Holtzkopf who wrote a wonderful book on pterygoids and zygomas. Definitely check it out. But you can see the prosthesis is very tall because she lost all of her maxilla. And there's no puck of zirconia that's taller than 35 millimeters. So I couldn't even fit her arch in a puck. So what did I do? I created a titanium substructure, and I cemented her zirconia into the titanium substructure. So I got strength from the titanium, decreased the weight because I wasn't as much zirconia. It was less expensive zirconia puck I needed to use because the thicker the zirconia puck, the more expensive it is. There's definitely less chance for distortion during sintering on a smaller puck, and there's greater flexibility on milling angulated channels through the titanium and the zirconia. So this woman, this is her before and after result, and this is her upper arch, and this is her smile. I mean, the upper arch goes all the way up to her nose. That's how much maxilla she lost. This is her before and after results. Her tissues, look at the long span here. And this is this titanium substructure. You can see it here in these images. I mean, this is going to last her for the length of time. And I also started, I'll go through the last couple slides quickly because I'm running out of time. So the main reasons for using titanium structures are greater than 2 ponics, kind of like an all-on-4 situation, extreme bruxisms. I want to get more rigid support. I also have affordability issues with some patients in South Louisiana. So what I started doing was milling titanium substructures and milling PMMA, like you see on this case on the bottom right. That's milled PMMA on top, cemented with a resin cement. This is a very, very, very strong full arch for this patient. And you know, later on, if she wears out the PMMA teeth, I just remill PMMA teeth and cement them onto the titanium bar. Or if later on in the future she says, you know what, I'm tired of PMMA, I want to go zirconia. Well, now I'll just mill it in zirconia and cement it onto the titanium substructure. So these titanium substructures are really, really awesome, and they're not difficult to work with. And a lot of times I need strength for my full upper arch, right? And sometimes the size of these people's arches are so big, it's just not going to fit in zirconia puck, and that's when titanium comes to the rescue, right? So this is a case I delivered for this patient here, her upper and lower arch, where we did PMMA, and she's an older female. She didn't want to pay for zirconia, so we made her a cheaper PMMA option that she loves, and she's happy. This is the arch I showed you guys earlier in the exocad drawing. These were the 2 second molars that wouldn't fit, so they're milled into the titanium substructure. This is the superstructure of zirconia, and this is that big old guy in his mouth, and this is his smile. This is it seated, fully torqued out. This was the drawing that I showed you earlier. I really should probably stop the webinar right here, and you just go ahead and start taking questions. Thanks for the time. I really appreciate it. Thanks, Ro, for having me. Thanks for sitting on this, and I hope I get a recorded version out to you guys pretty soon. I will mention that I'm going to give, just for this webinar, I'll give 25% off on the first 100 orders that come through. So click on this QR code, go to checkout, and message me on social media. I'll give you a little discount code whenever you want to buy some of these screws. Hope this video helped you guys out. Thanks so much for having me. All right, we'll take some questions.